Hello to you all Ansys Fluent users and CFD enthusiasts. Welcome to CFD Land. In this study, we're going to investigate and validate the Blazes exact solution for the gamma layer on a flat plate. But prior to the CFD solution, we're going to have a brief look on the description of Blazes exact solution to know what exactly it is and how it can help us. Let's start by the definition of Blazes exact solution for the gamma layer on a flat plate. It's actually a fundamental concept in fluid dynamics. You may wonder why you just call it fundamental. Because it provides a similar answer to the gamma layer equation for laminar flow over a semi-infinite flat plate. This answer, the answer that can be reached by Blazes exact solution, gives us a way to speculate about the velocity profile and thickness of the boundary layer in these planes of flows. One of the intriguing points about this solution, at least for me, was that it was found by Heinrich Blazes over a century ago. It is actually surprising. So, how it works? The Blazes solution utilizes a similarity variable called eta to transform the partial differential equation of the down letter into a single ordinary differential equation, which can be solved numerically as well. The aim of conducting the present CFD solution and comparing it with the Blazes solution is to validate the numerical model's accuracy in predicting down layer behavior. Well, this is the schematic of our computational domain in the current CFD simulation. As you can see, it is extended for 1 meter in the x direction and for a half a meter in y direction. The water flow will enter a domain from the left boundary side. The 10 meters per second lost the magnitude. On the right side, we've got an outlet. On top, there is a symmetry boundary. And finally, the bottom side, which is evolved with no asphyxia condition applied on that. So the water flow will be able to establish a boundary layer on that. As you can see, a point is specified near the outlet region, in which we're going to investigate the velocity profile, both with Blazes exact solution and also our CFD simulation. So you can see the coordination of this point with x and y values of 0.96 and 0.3099. Regarding 10 meters per second uniform velocity magnitude and also kinematic viscosity of water liquid, eta is calculated. It equals 3.2. Next, based on the tabulated Blazes solution table, 3 variables including f, f prime, and f double prime should be calculated. So, as can be seen in this table, we've got all 3 variables, and now we're able to have the velocity profile based on its relation with f prime. So, considering all of our assumptions and variables, the predicted velocity is equal to 8.7461 meters per second. Alright, it's time to make all those stuff into practice via Ansys Workbench. So I'm going to explain from A to Z, so this training video would be appropriate for all users, including beginners. So this is the Ansys Workbench workspace, which can be opened through the Serve toolbar of the Windows. You just need to search for Workbench, and just by clicking on that, you can have that. As you can see, the version that I'm using right now is 2024 R2. Alright, so let's start from this workspace. As you know, we need to drag and drop the Fluent flow with the Fluent software module into the blank space, and this module can be found on the toolbox on the left side of the window, and all you need to do is to just drag and drop it on the blank space. So you can see that the software describes several steps for you, starting from geometry up to the results. So let's start by geometry. As I'm going to use Design Modeler software in order to draw the computational domain, I need to right-click on geometry and then click on New Design Modeler Geometry. Well, this is a modular environment in which you can see the tree outline on the left side, consisting of all three main planes, including XY and ZX and YZ. So what I'm gonna do is to draw a rectangular domain in XY plane. So first of all, I click on Z origin on these right sides, so I can normalize the view on XY plane. And then, as you can see in the ruler, which is extended from 0 up to 30 meter, this is actually so much for us in order to draw a long meter in length rectangle. So what I'm gonna do is to zoom a little bit, so I'm gonna have a more suitable scale. In order to zoom, you can use the wheel mouse on your mouse, actually, or you can drag and drop a rectangle by pressing your right click on the mouse, so you can zoom with this option. So you can see that we could zoom in, and now the scale is extended from 0 up to 4 meters. All right, so one more thing that I can mention here is that you can change the location of your view by holding down the Ctrl key on your keyboard and then pressing the V mouse on your mouse. Now you can see that I can change my view. It's something handy during our design. Alright, so let's start drawing the geometry. First of all, I click on XY plane and then click on New Sketch option so I can have and draw the sketch font. Then in the sketching tab, you will have plenty of options in order to draw geometries. But you already know that what I need in here is a rectangle. So I pick rectangle option. And now I am able to click on the origin and draw the rectangle. So I click on the first point, and then I have to click and define the other point. So it would be somewhere around here. Considering 4 meters of scale, it should be something like this. All right. So one more important thing that you can keep in mind is that you can see the coordination of the mouse right here on the right side. Below here, you can see the coordination. So don't forget to select exactly the origin at 0, 0. Alright, now it's time to define the exact dimensions. So in the dimensions tab, you will have plenty of options to define the actually dimensions. But on top of it, you have a semi-automatic option which can help you to have a fully defined sketch. So just by clicking on that, you can see the software automatically let me know which parameters I need to define. So first thing is the height of my rectangle, and the other one is the length of that. And it is ended. You can see that by describing and defining L1 and L2, I can have a fully defined sketch. So in this table, I can put 0.5 meters for L1, which is the height of the rectangle, and actually for length of that, I've got 1 meter. Alright, so just back to the generate button, I can create a sketching tab to the modeling tab. So this is the outline of my domain, but I need to convert it into a surface because actually in 2D simulations, we need a surfaces to define our computational zone. So in order to convert it, I can have it from concept tab, surfaces from a sketches option. Only by clicking on the sketch one and then apply that, I can have my base object as a sketch one, and you don't need to define anything else but to click on generate button. Now I've got my computational domain. As you can see, a rectangle with 1 meter in length and 0.5 meter in height. And you can see beneath the parts that we've got a surface body, and right here I can change the name. So I rename it. I can call it flat plate, for example. And one more thing that can be changed in here is the fluid or solid. Of course, we know that this is a fluid zone, so I can simply select fluid down here. this is done, I can say that we don't have to do anything else in Design Builder software. So I quit this software and instead double-click on Mesh in order to open Ansys Meshing software. Well, in Ansys Meshing, we have to do two major steps. One is the production of grid, and the other one is to define boundary conditions for the use later in Solver. So let's start by the step one, which is the production of mesh grid. So as I click on mesh, you can have access to the parameters related to the mesh grid, but actually I'm going to create a structured grid. So I'm going to have a specific number of divisions over each of these edges, and by just connecting all of those together, we can have a high qualified structured grid. So let's start by defining a sizing for each of these boundaries. So just by clicking on mesh and then insert sizing, I have to select each of the edges that I'm going to define element size or the number of divisions for that. And for selecting each of these edges, I have to pick edge selection option up here in this toolbar. So now I'm able to click on each of these edges and select it. So for elet in alpha boundary, I'm going to have the same number of divisions with a particular pattern. So by just click on inlet and then holding down the control key on my keyboard in order to have a multiple selection, I can select both edges and apply them. Now it's time to define the number of or the size of elements, but what I'm going to do is to define number of divisions. And for these two edges, I'm going to have 120 divisions, just like this. But regarding the fact that we're going to investigate the flow pattern on the boundary layer, on this wall, we need to have denser structured grid near this wall, not on the top side. So what I'm going to do is to define the bias for this division, and you can find this up here in this bias type. By just changing that to the first type, I can have denser grid on one side and actually limited grid on the other side. So for bias factor, I'm going to define the 100. So now you can see that it is totally appropriate. The number of divisions is limited on the upside, but it is denser near the wall vision. But for the other side, it is not correct. And you can see that it is completely inverse. So I have to use reverse bias option down here, click on no selection, and instead select these alpha boundary and apply that. Now the denser grid is near the wall region. This is actually what is suited for our simulation. But there is one more thing that I'm not gonna use the curvature or so many other options that the software uses in order to generate grid. I'm going to have my own specifications. So I'm going to turn capture curvature option off by just turning it into no option, and instead change the behavior to the hard. So the software will just follow my lead. So this was the first insert option. I need to have another one for the up and down wall, and this time I'm going to select these two edges. And once again, I need to change the element size to number of divisions. So for the length of this rectangle, I'm going to define a higher value, higher number of division. This time, maybe 220 would be appropriate. And of course, the distribution is going to be uniform. I'm not going to have any bias this time. Because the number of divisions across these lengths of the rectangle is important. And I don't need to have any focus on a specific region. But once again, change the capture curvature option to the no and change the behavior to the hard. we have to follow one more leading here to make sure that the software automatically generate a structured grid with quadrilateral cells. And this time I'm going to insert face meshing option. So this time I have to select the surface. So as you can see up here, the face selection option is activated, and now I'm able to select the face and apply that. And the default method is on quadrilateral option, and this is actually what we needed in here in order to generate the structured grid. So after all, get back to the mesh and click on Generate Bot. So you can see the process is loading, and the software is trying to use these options to generate these high quality grid. And you can see that the quadrilateral cells are more denser near the ball region, and this is exactly what we were seeking. So I can say that our generation of the grid is ended, and we can get to the second step, which is defining the boundaries. But before that, in here, I mean, in the statistics part, you can see the total number of elements. It's 26,400 number of elements, which is not very high. And this is, I think, I consider it as sufficient. So let's define each of the boundaries for the use in this solver. In order to do so, I'm going to select each of the boundaries, and of course, in a three-dimensional simulation, the boundaries would be edges. So once again, I select edge selection option in order to select the inlet boundary, and just by selecting that and right-click on the blank space, I can have create net selection option. Now the software asks for a name for this boundary. I'm going to call this inlet, for example, so you can see in the tree outline, the name selection is added. And we only got inlet boundary for now. So I'm going to repeat this task and define outlet boundary, and also the wall, and finally the upper wall, which would be a symmetry boundary. I will discuss it later, but for now, let's just call this symmetry, so the software will automatically use symmetry boundary condition for that. So it is ended, and we can create Ansys meshing as well. Alright, so you can see that it is not updated, and just by right-clicking on that and click on Update button, the software will automatically transfer the mesh that is generated into the solver. Now, as you can see, it is checked, and we can double-click on Setup in order to open the Ansys Launcher. So first of all, do not forget to check the double precision option. By using this option, the software will use 64 bits to store numerical values instead of 32, and this will result in 15 or up to 17 decimal digits of precision. So it can help for the accuracy of our simulation. And considering the power of your CPU, you can increase the number of processors. For example, for my system, I'm going to use 4 processors in order to use in this simulation. Now, the Ansys Fluent is loaded, and we can start by general settings of the software. As shown in this window, the software generally asks for 2 main settings related to the solver. One is the solver type, and the other one is the time mode. So let's start by the solver type, including pressure-based and density-based solvers. In pressure-based solver, we are assuming incompressible fluid or low speed flows in which the Mach number is usually less than 0.3. So in these cases, we can assume that the density is negligible, and we can avoid the change in density. But for the cases with high speed flows or where the compressible flows are actually included, we cannot neglect the density changes. So these can directly affect the momentum and mass and energy conservation. So this is actually mostly seen in aerospace application or aerodynamics or combustion processes. So for this relation, we keep the pressure-based solver, and now let's move on to the time mob. And the distinction between a steady and transient time modes is actually fundamental. These modes describe how a system's properties change over time, which in turn affects the form of the governing equations, including Navier-Stokes equations or energy equation. So for this simulation, we already know that a steady state condition is governed, and we have to keep a steady state time mode in which the variables, including velocity, temperature, pressure, and so many other variables, are not changed with time. Now it's time to define the turbulence model. So expand the model section and double-click on viscous style. In this window, you can see different turbulence models are given by Ansys Fluent. First thing we need to keep in mind is that the Reynolds number in our simulation regarding the inlet velocity, the characteristic length, the viscosity of the water liquid, and also the density of that, the Reynolds is much higher than 5 and multiplied by 10 to the power of 5, which is actually the criteria for transition between laminar flow regime into the turbulent regime on a flat plate. So we need to use turbulence model, but which one are we going to use? Actually, turbulence models in Ansys Fluent range from the simple one equation as Pollard-Alvarez model up to two equations like k epsilon or k omegas, up to more accurate turbulence models. But for this relation, we're going to use k omega SST model. The k omega SST, which stands for shear stress transport model, combines the best features of k epsilon and k omega models. And using k omega near walls and k epsilon near the shear seams, making it particularly effective at predicting flow separation under adverse pressure gradients. So it is best suited for actually aerospace and turbo machinery application because it prefers an excellent balance between accuracy and computational cost, especially for boundary layer flows, which is actually our focus in this simulation. So I'm gonna keep k omega SSC. Next, it's time to define our working fluid, which is water liquid. So I close model section and instead double-click on material section. So as can be seen in here, Ansys Fluent by default has actually air as the fluid and aluminum for the solid. So I have to create a new material, which is water liquid. So I click on Create or Edit button, and in here I can change the name of our fluid and define manually the properties of water liquid. I mean the density and viscosity of that. But because water liquid is one of the widely used materials in the industry and simulations, we can have access to that in Fluent database. Actually, these are some predefined materials, including acetone, for example, up to water liquid. So you can find water liquid as you scroll down, and just by clicking on water liquid and then click on copy button, I can have that on my list. You can see in here. So there is no need to change the properties now. I've got water liquid in here, and you can see that the density and viscosity is already set. But it is not done yet. I have to apply that on my computational zone. So in cell zone condition, you can have access to your one and only flat plate zone. And then in the settings part, you can have the material name. But because we have two options, we've got two defined liquids, fluids, I have to select water liquid right here. So from now on, just by applying that, the water liquid will be filled in our domain. Next, it's time for the boundary conditions. So let me change the view to the zoom tab so you can see the number of boundaries dedicated to each of the inlets, outlets, and the walls. And on top of it, let's start by inlet boundary. So you can see by default Ansys Fluent use velocity inlet type boundary condition, but you can actually change that. Because I'm going to define velocity magnitude for this blue boundary, which represents inlet boundary, I'm going to achieve velocity inlet type boundary condition. So just by clicking on edit button, I can have access to the settings related to this boundary. So for inlet boundary, I have to define velocity magnitude of 10 meters per second, but I'm going to have it through the x coordination. I mean, this 10 meter is actually x component of our velocity. So I can change the velocity specification method to the components, and then I can have and define the velocity in each of the directions individually. So for x velocity, I'm going to define 10 meters per second, and I keep it as 0 for y direction. And actually, you are not going to change anything else in here, and apply all of these settings and close these settings. Now it's time for the outlet boundary, which is shown by red color. And by default, Ansys Fluent uses pressure outlet type boundary condition. This is actually, again, what I need. So I simply click on edit button, and in here, the software asks for the gauge pressure, which is the most important parameter in pressure outlet type boundary conditions. So considering that this boundary will, water liquid will exit a computational domain to environmental pressure, I'm going to achieve zero gauge pressure, which means that the atmospheric pressure is set on this outlet boundary. And this is actually not gonna affect our results. So I keep that and apply that. Finally, before getting to the wall boundary, you can see that the software automatically uses symmetry type boundary condition for the symmetry boundary. As you may remember, in Ansys meshing, we define symmetry name and call this absolute wall as symmetry. This is where it can help. So what is a symmetry boundary? Actually, it acts like a mirror. So this software will consider no normal velocity or normal variable on this plane. So it will actually act like a mirror, and this can reduce that computational cost. And finally, it's time for a wall boundary, which is a bottom side. So let's just see and check the settings. As you can see in here, the wall motion is set on a stationary wall because we always know that it is not moving. So I keep the settings. And the most important and notable part in here is the noise dipshare condition, which is actually the main reason of establishment of the boundary condition. Boundary layer. So I'm going to keep that and apply that and close this section as well. Hopefully the setup section is completely done, then we can proceed to the solution section. And on top of it, the message tab. So by double-click on that, you will have access to pressure velocity coupling schemes offered by Ansys Fluent, and also a special discretization of each of the terms and equations. So for now, let's just focus and concentrate on pressure velocity coupling schemes. As you can see in here, Ansys Fluent offers us 4 different schemes. And regarding the fact that we're going to use couple algorithm, let's just have a brief description about that. This algorithm actually that is employed for pressure velocity coupling solves the momentum and the continuity equation simultaneously in a coupled matrix system. So by using this approach, we can expect a faster convergence compared to the other algorithms that are called segregated algorithms. And then for a special discretization, first for pressure gradient, we're going to use second order And then for momentum equation, second order of mean for its higher torusy in order to capture the velocity field. And finally, for both turbulence transport equations, again, we're going to employ second order of in the scheme. All right, now it's time to expand monitor section to check the visuals. So you may wonder what are these visuals. Actually, these visuals are numerical measures that actually indicate how far our solution is from exact convergence, representing the error in the equations. So these are some criteria in order to check the convergence of our solution. But you should know that these are not the absolute criteria. I mean, they don't guarantee our convergence. So these are just primary convergence criteria. For these results, I'm going to define another absolute criteria, 1 to the 10 power minus, let's just say 5, and do it for all the equations. So as soon as all the residuals will reach these absolute criteria, the solution will be automatically stopped. All right. So next, it's time for initialization. Of course, for actually, let's just say starting the solution, we need initial guess to put into the equations because, as you know, in CFD we are using an iterative solution. So in order to start, I'm going to use the standard initialization method and compute all the values from the inlet boundary. So just by clicking on initialize button, the software will automatically use a kind of uniform distribution for all the variables in the equations. And actually, these can help us through faster convergence. All right, now it's the last step, and we can start the calculation from run calculation part. The software asks for a number of iterations, so let's just keep 200 from now and click on calculate button. All right, just after 120 iterations, the solution is completely converged regarding the primary convergence criteria or residuals. So you can see the latest iterations that the residuals could reach higher than, or let's better say, lower than 1 to the 10 power minus 5 that we've defined for absolute criteria. All right, so let's just check the results. On top of it, I wanna check the contours in order to check the boundary layer and how it is formed during the water flow over the flat plate. So in the graphic section, you will find contours. In this window, you've got access to many different variables, including pressure, density, velocity, or some turbulence-related variables. But what I'm going to check for now is the velocity streams. And in the surfaces box, I'm not gonna display it over a specific boundary. I wanna check the velocity over all nodes of the computation domain. So I can select all of them or none of them. So I keep this default choice and just display them. So you can see the distribution on velocity across our domain. So let me zoom a little bit. Now you can have a better view of how the boundary layer is formed near the bottom wall with no associated condition of that. So you can see right now the velocity is 0 on this wall due to existence of no associated condition. And as we move toward the upside, the velocity will be increased up to 10 meters per second, where it is reached our inlet uniform velocity. For another type of visualization, we can use the velocity vectors. I show you. But for now, let's just check other variables such as pressure. You can see the pressure increases drastically as the flow enters the domain, but over time it reaches the alpha pressure or atmosphere pressure. So let's check the vectors or velocity vectors. The settings is just the same. You can color the velocity vectors by different variables, but for now I want to cheat and color these arrows with velocity magnitude. So let's just display them. And in here, let's just zoom in a little bit. And these are the velocity vectors. And you can see the velocity profile very clear in here. But of course, in order to investigate the Blasius exact solution, we calculated the velocity magnitude at a specific point. So we need to define a point right here with exact coordination, and then report the value on that. I mean, the velocity value on that. So what I'm going to do for now, from Dunning tab, I'm going to create a point. So the software asks for the name of this point. I'm gonna keep 0.6, and for coordination of this a specific point, the x would be 0.96, and then the y value 30 and then 99. And don't forget that we are calling this 0.6. So as I create that, I can use that in our reports. So down here in the report section, as you expand that, you've got access to surface integrals. So first thing that software asks is the report type. Of course, we've got plenty of options regarding different type of report sets we can use based on our need. But for now, because I'm going to report this velocity or variable on a specific point, I have to use vertex average type. And now the software asks for the variable. Of course, I'm going to report velocity, but this time I have to select my specific boundary. In our case, I'm going to report that on 0.6. So simply select that and finally click on compute button. So here it is. You can see the reported velocity magnitude on these vertex. And as you may remember, we calculated that for based on Blasius exact solution that led to 8.767461 meters per second. It means that they've got about 20% error in this. So you may wonder why the error is so high. Maybe 20% is not that much acceptable. So there are several reasons that I'm gonna discuss here. The first thing is that the mesh generation or the grid specifically near the boundary layer is very crucial for this investigation. You need to use finer mesh and then again simulate these solution and then check the results in order to check if we could have reached the grid independence values or not. The next point is that the Blasius exact solution is dedicated to laminar flow regimes, but in our simulation regarding the 10 meters per second velocity at the inlet boundary, we can calculate the wrangles, and we already know that we have a turbulent regime flow. So Blasius doesn't work anymore here, but still we could have reached 20% error. So you have to decrease the velocity inlet in order to keep the laminar flow regime and prevent any transition to turbulent flow. And then you can investigate the Blasius solution once more. And these are just two main reasons for this 20% error.